Alright, here I'll just run over a quick frequency response where we try the accelerometer across the frequency spectrum from around 100 Hz to 10 kHz. We can see here the block diagram of the test setup. We have the tone generator we saw before, the small amplifier and mechanical exciter. What comes out of the mechanical exciter is some mechanical movement in form of acceleration, but the exciter is basically just a pretty simple speaker, and it's not linear, and it's not very good for producing high frequency vibrations. So we expect it to be best in a relative low frequency range, and we also know from motion physics that the lower the frequency of acceleration, the bigger movement. So I expect the frequency to be most significant at lower frequencies. The exciter is connected to the accelerometer, sends the signal through the filter. It gets digitized by the analog to digital converter. An FFT of 1024 bins or frequency intervals is made. The data is sent to a PC. The first test here is limited to 10 kHz to get a reasonable resolution on the size of the frequency bins, and we might do a test where we run it up to 20 kHz afterwards. So right now we don't have any input signal. I'll turn up the signal generator here, and we can see something starts to happen at around 100 Hz or so. And as I turn up the frequency, the amplitude goes up as well. We can see down here in the histogram that the frequency follows up. And I'll just give it another decade. On the way there are some harmonics we can see from the frequency, but that's probably due to mechanics. And here the exciter is not that powerful anymore. We can see the amplitude is decreasing a little. So I'll try to turn up the amplification a bit. Right now we are at 8 kHz, 9, and the exciter is not that good at vibrating anymore because it's a low frequency speaker. I'll turn it down again.